So in this problem we have this object. It's a sphere with a cavity. The sphere has radius r, and the cavity has radius a, and the charge density is rho. So this object of a sphere with a cavity is equivalent to having two separate objects, to having a solid sphere that has radius a and charge density rho, and a little sphere that has charge density negative rho. Because if you add those two objects together, it's equivalent to having the sphere with the cavity, because the charge densities cancel out. So if we calculate the electric field of those two separate objects and add them, it's the same as having the electric field of the sphere with cavity. So let's look at the solid sphere first, charge density rho. And the electric field inside the solid sphere is given by Gauss's law. This is Gauss's law. Okay, so if we just draw a Gaussian surface inside this solid sphere like this, we can calculate the electric field at that Gaussian surface. So we just multiply the electric field by the area of the Gaussian surface. And the charge enclosed inside the Gaussian surface is given by the charge density times the volume inside the Gaussian surface. So we just put in what is the area of the Gaussian surface and what is the volume inside the Gaussian surface. And then we can calculate what the electric field is. Okay, so it's given by this. And it points radially outward. So that's the electric field inside this solid sphere. It depends on how far you are from the origin. So if we write it as a vector, we can write it like this, where the vector r is the vector from the center of the sphere to the position where we want to measure the electric field. Okay, and we call this E plus. So this is the electric field produced by this positively charged solid sphere. Okay, so now let's look at the other object that we were interested in, this little sphere. So we had this sphere with a cavity is equivalent to adding the two objects. Now we look at the little object, the negatively charged sphere. What is the electric field inside this little sphere? Well, it's given by Gauss's law also. Okay, so if we draw a Gaussian surface inside this little sphere of charge density negative rho, we can calculate the electric field where that Gaussian surface is. So the electric field is given by this. We plug in the charge inside this Gaussian surface is given by the charge density times the volume. We plug in what the area is of the Gaussian surface and what the volume enclosed by the Gaussian surface is, and we get that. And then we just have to find what we solve for E. The electric field at that Gaussian surface is given by that. So it also depends on R, and it points radially outward. But here R is the distance from the center of this little sphere to the point where we want to measure the field. Okay, so the origin of this r is the center of that sphere. So we'll call that r nu. That's a nu vector. And then if we write the electric field as a vector, r nu is that vector that points from the center of that sphere to the point where we want to measure the field. So let's call this field E minus, and this represents the total field produced by the negatively charged little sphere. So now the total field of this sphere with a cavity, which is equal to the sum of the fields produced by the solid sphere of charge density rho and the field of the negatively charged little sphere. So we add these two fields, E plus and E minus, and that gives us the total field of the sphere with a cavity. Okay, so the total field is equal to E plus plus E minus. And what are those values? Well, E plus is we found was given by that, and E minus is given by that. So r nu, remember, what is r nu? Remember, it's the vector from the center of the little sphere to the point where we want to measure the field. Okay, so let's draw this. If we have, that's the cavity, this vector is r. It's a vector from the center of the sphere to where we want to measure the field. The vector a goes from the center of the big sphere to the center of the cavity, and r nu goes from the center of the little sphere to the point where we measure the field. So r is a plus r nu. Okay, so that means that r nu is equal to capital R minus a. So if we just plug that into r nu, we have an expression for the total electric field inside the cavity. Okay, we plug in r nu, and then two of these terms cancel out, so we find that the total electric field inside the cavity is just given by this. Okay, so the vector A is actually of magnitude A and pointing in the j direction. We can just write it out as that. So that means that the total field inside the cavity is just a constant. It's just rho A over 3 epsilon naught in the y direction. This is the total field inside the cavity.